knowledge about PMU was probably a visit by Arun to University of Washington. And that was in late 80s or early 90s, I think. And then I remember he was talking about this, I think that equation shown earlier, that I probably have seen it at that time. And then, of course, the early conclusion is the state estimation is going to be linear. So it's going to solve all your problems. And it happens, I was teaching state estimation, and that was an iterative method. So I begin to feel maybe I have to cover it in my class about PMU. And then at the same time, about the same time, I went and visited Bonneville Relay Labs. And I saw Ken Martin, he has his gadget toy with, sitting on the rack. And he was showing me that's the satellite time. I was not doing that project, but I was doing relay project. But I think I was sold by that time. Then, of course, I did my dissertation at Berkeley, so the largest power system in my dissertation is also 3-bus. However, I was a little bit more defensive than Sheldon, because at my time, next to me there was a student. He's also doing his Ph.D. And one day we were talking about these questions on conference. They always ask, how come you didn't test it with a 500-bus system? And my colleague sitting next to me, he would tell me, don't worry, the power system in Libya has 3 buses. Now, it took me more than 10 years to be upgraded, because then I was working on some defense system. I'll get to that later. And finally, I got help from Mike Hoffman and Bonneville Power. And we were looking for the undesirable tripping of the zone 3 relays. And we got 15,000 bus system data. So it took me a while to be upgraded to a 15-bus system. But I should say the trigger was when we were working on a project in the late 90s, we started to work on the cascading failure and catastrophic outages. And so the main idea was, one, we have PMUs. This is at late 90s. And then two, we have this concept of wide area protection and control. And so we put together a nice team. And of course, the spiritual leader of PMU and the wide area protection is Arun, and indirectly Jim. Now, this is good for my research because why? The last several years, I've been going to China. I made a few visits to China. And then every time I go, they will ask me, I will ask them, what do you want me to talk about? And most of the time, they will tell me, oh, your paper in the year 2000 about defense system, they all know that. Can you come and talk about that? And well, to be honest, the real contributor of that paper was Arun. So I have to confess that his work is making an impact not just on me, but it's very broad-based in other countries. So with this, what did we do? Then of course we have PMUs. So I'll come back here. So there are a number of questions we had to answer to be able to say, okay, here is a self-heating power system. And that was the main subject at that time. What is, given the wide area protection and control problems and the PMUs, can we create a new generation of technology called self-heating power grids? And that was the theme. So ever since then, I've been thinking about that question. What is a self-heating power grid? And I don't think there's a very good and very commonly adopted definition as of today. But that is something that has made a big impact on my research directions. So the first question is, how do you know the system is vulnerable? We're looking for vulnerabilities, and vulnerability comes from different ways. So there is a first vulnerability. This vulnerability is about the system dynamics. It's loss of synchronism. And what happened is, I asked the student to go sort through the blackout reports and then find me some vulnerable patterns of cascading. So what will trigger another? These patterns. One of them is loss of synchronism. There are other things like zone 3 tripping, undesirable tripping or zone 3 relays. There's a tripping due to overexcitation generators. And there are a couple other things, but we went through the blackout report to find these patterns. These are not probabilistic. These are most likely driven by the physics, which means one will lead to the other. And that, I think, will contribute to this. And so then here is where I run into Jim Thorp again. So we were looking for the waveforms, looking for something that will tell me about the waveform stability of the PMU acquired data. So we look at the PMU data window, and we were trying to say, okay, now you look at this waveform, what do you say about that? And then we went to the papers, Jim Thorp, and I think from colleagues at Cornell University as well, on the Lyapunov exponents. And so we explored the Lyapunov exponent a little bit about how to do that. And so, and there is a picture of the 200 bus system, not the 3. And so essentially this is what we were able to say. If you look at the dynamics, if you want to look at the contingencies one by one, just like what we've been doing for years, then looking at the waveform and after the contingency, look at the waveform and see if you can say something about the stability of that waveform, which means that waveform, is it going to continue the trend or is it going to fly away? And that, I think, is what we get out of that. So for different kinds of contingencies, you'll be able to assess the stability of each contingency based on the Lyapunov exponent. So that at least provides some partial answer to a question, how vulnerable is the power system? And then the next one is, all right, if it's vulnerable, then what do you do? So in an emergency condition, if it's really emergency condition, maybe you want to split the grid. And so we have done work on how to split the grid. That's partitioning the grid into more than one subsystem. That was the one concept. But then there's one more question that comes before that. Even if you know how to partition the grid, and I think there are papers in the literature on that, and I think we work quite a bit on that, there is still a big question of when do you do it? I mean, you're watching PMU, imagine you're an operator sitting here watching PMU. When do you develop enough guts to say, okay, I'm going to open that and the system is going to be split? Very few people got award for avoiding a blackout because you cannot prove there will be a blackout. All right, so we have to answer the first question, which is where, and this is just to say if I don't do anything, the whole thing will collapse. All right, so what do I do then? So this picture says, well, how about this? We will use that Lyapunov exponent as a tool, and that will tell me how system dynamics is moving. And if I watch the index, at some point the index begins to tell me instability trend is coming. And that will be the good time to trip. And it turns out, at that time of partitioning, one generator just quit because of overexcitation, and that was the point. Right after a generator trip, the system becomes very vulnerable, and that's what this dip is, right? So that answers one question, and then the second question is how do I partition? And that will be an easier question. So then you have to work out different kinds of partitioning algorithm. And I would just say there are different kinds of partitioning algorithm, but I just say computation itself is not the bottleneck of this. Because we have tried 22,000 buses, and figuring out the partition, that takes very little time. So let me come to the next question then, which is another form of cascading. Generator can trip because the reactive power burden is too high. And it's too high because it's working very hard to support the low voltage profile. And if it works too hard, it quits. If it quits, then other generator will become the problem, the next victim. And so it does create a big, cascading from there. And so the natural question is, can you see that then? Now that you have all that data, can you see that coming? Because this is what cascading event is about. Can you see that coming? It's much easier to see it after the fact, right? All right, so here is the thinking. How do I know the field circuit of a generator is going to trip? Well, if it's, let's say, the protection will probably have characteristics like this. This is just an overcurrent protection characteristic. And this is hidden in the power plant. And if the overcurrent gets the field circuit to be too hot, then it might trip. And that might give you one clue about which generator might trip. In this condition, that's one thing. Two is, can we compute this? Can we compute this? And the answer is, what may be? Because we are already doing a lot of computation online for these contingencies. These contingencies have not happened yet, but we are doing that because of n-1, n-2, etc. And so if you already have all the computation, can you just take one more step into the power plant, calculate the field circuit, and look at the relay characteristic and tell me which one might trip? That will increase the n-1, n-2, to n-2 or n-3, and tell me the cascading. So this is the experiment we have done, and there are some details, but essentially what you can do is to see what could you have done to try to prevent the cascading. And in this particular example, what we found is, if I can find which generator might trip based on the concept that I have talked about, we have simulated that. If I can do that, then at that time, then I would know which generator might be in trouble, right? And so if I want to do this self-heating action, perhaps what I should do is try to reduce the burden of that generator, right? And how do I reduce the burden of that generator? Well, I try to reduce the voltage by a little bit. And in this particular example, it shows if I'm able to, if I reduce the voltage by 3.03, which is 3%-ish, then I could have prevented a cascading relay tripping due to overexcitation generators. So this is really a line of study about cascading failure and defense. And I must say that I have benefited a lot from the inspirational mentorship from both Arun and Jim. Early on in my career, I have talked to Jim in his conferences, particularly circuit system or control conferences, and every conversation, however brief, it has really benefits from my work. And I think both of them have a very unique and straightforward way to make sure you turn to the right direction. Thank you very much.